Welcome back to ChemDoctor, and this would be the third video in the playlist on reviewing theoretical yields and limiting reactant, and it's part of the playlist that deals with theoretical yield and limiting reactants. Now, these are long problems, and what I recommend that you do is have out a periodic table, a calculator, and a piece of paper, and you should follow along and do the calculations as I do them in order to get the most out of this. And then the other thing is that you need to make sure that you thoroughly understand the concept of theoretical yield, and in other words, being able to calculate the mass of a product produced in a reaction given a certain quantity of reactant. And you should be able or be very comfortable with finding the mass of the other reactant that reacts with whatever you were given. So don't try to jump right into this, and I would highly recommend that if you're not comfortable with a basic theoretical yield calculation, that you go back and view those videos and learn those concepts before you try this one. Now, the limiting reactant basically has to do with a situation where you're given either mole or mass quantities of all the reactants that are shown in the equation. And we're going to start this example with an easy reaction where there are only two reactants and one product, so that we can literally just focus on the relationship between these two reactants. And since there's not more products present in the reaction, we only have one product to worry about. Now, before we begin this, what I want to do is establish the molar masses of everything that's in the equation here, because we're going to be needing that information. So the aluminum, if you look at a periodic table, is 26.98 grams per mole. The oxygen, being diatomic, is 32. And the aluminum oxide the total is 101.96. So I'm going to put these numbers up here so that we can extract them easily as we do this. Now, there are a lot of different procedures or methods to calculate or determine a limiting reactant, and the method that I'm going to use here is the one that I think is the best. And I think you'll agree if you try it and you learn it, and then later down the road you can look at some of the other methods. What makes this one the best is that you don't have to evaluate ratios of reactants in order to decide which of these two reactants is going to be the one that runs out first. And that brings me to another important point. When we use the term limiting reactant, what we mean to say is that one of these two reactants is present in amounts which is small compared to the other one. So what's going to happen is that reactant is going to run out, and when it does, then the reaction comes to a stop. So the limiting reactant is the one that controls the theoretical yield of the reaction, and in this case we're going to be solving for the aluminum oxide that's produced in mass. All right. So the limiting reactant controls how much of this that we make, and it also controls how much of the other reactant is used in the reaction. And by determining the limiting reactant, we can figure out which of the two reactants is the one that is in excess. Okay, so we're going to do two things in this problem. We're going to figure out the limiting reactant. We're going to calculate, so we're going to do three things in this video. We're going to determine the limiting reactant. We're going to calculate the mass of the product that's produced, and we're going to figure out the mass of the remaining reactant, how much of the other reactant is left over. All right, now to do that, we're going to calculate the theoretical yield of the aluminum oxide using both reactants. And we're going to see which one of these two reactants produces a smaller amount of the product. And whichever of the two reactants produces a smaller amount of the product, aluminum oxide, that reactant is the limiting reactant. Now, this is an easier type of limiting reactant problem because the two reactants have been given to us in the form of moles, which, to remind the viewer, is in the same units as the coefficients from the balanced equation. So we can start right in by converting the aluminum and the oxygen into aluminum oxide using the ratio from the balanced equation. So what we're going to do is put what it is we're solving for in the numerator or in the top of this fraction. And again, we're solving the theoretical yield in moles of aluminum oxide using both reactants. Now we see for the aluminum it's 4 ALs in the bottom here. All right, and for the oxygen it's 3 O2s. All right, and these are the ratios from the balanced equation. All right, and what we're going to get will be we're going to produce 0.01 moles of Al2O3 using the aluminum, and we're going to produce 0.0133 moles of aluminum oxide from the oxygen. So it's only at this point in a limiting reactant problem that you can judge which of the two reactants is limiting. And the way we do that is by comparing this number, the moles of aluminum oxide produced by the aluminum, to this number, the moles of aluminum oxide produced by the water. And you can see that the moles of aluminum oxide produced by the oxygen is greater than the moles of aluminum oxide produced by the aluminum. So I'm going to come back over here and circle this. The aluminum is the limiting reactant, and I will abbreviate that as LR. This is the limiting reactant. So now, the second goal of this was to find the mass of aluminum oxide produced. So we're literally one step away from that. All we need to do is multiply the aluminum oxide times the molar mass of the aluminum oxide, which is 101.96 grams per mole. So the mass of aluminum oxide that we're going to produce in this reaction is going to be 1.02 grams of Al2O3. All right, and this is our theoretical yield. This is our theo yield, and it's based on the limiting reactant. If you calculate this off of the oxygen accidentally, then you will be violating the laws of the law of conservation of mass. In other words, you would be getting out more aluminum oxide than is possible in this reaction, because the fact that the aluminum is the limiting reactant means that it's going to run out before the oxygen. All right, now the next thing that we're going to do is I want to calculate how much how much oxygen reacted with the aluminum, and then we're going to use that value to figure out how much of this oxygen remains after the reaction. Now, we can draw an analogy to what I want to do next. So if we had, for example, a car body, and which would be analogous to the aluminum, and the oxygen represents the tires that we're going to put onto that car. Remember that what we just figured out, the aluminum is a limiting reactant. That means the oxygen is in excess. So if the aluminum was a car body, that would be similar to the idea where maybe we've got 7 tires representing the oxygen. It's in excess. We're going to use 4 of those tires, and that would mean that there would be 3 left over. So what it is I want to do now is I want to find out how much oxygen is going to be left over. And to do that, we first have to figure out how much oxygen, how many tires actually go on the car body. Now, to figure this out, you must use the limiting reactant. So I'm going to pull down the moles of the aluminum, and we're going to use a ratio from the balanced equation again to figure out how much oxygen actually reacted with the aluminum. And so we use a ratio from the balanced equation again. We see that there are 3 O2s that are used for every 4 aluminums that react. All right, and what we get is 0.015 moles of oxygen. Now, this is the oxygen that's used up. Used up in the reaction by aluminum. I'll make sure there's a really good label on this. All right, and this is basically the number of tires that went on the car body. Now, notice that what we went into the reaction with was 0.02 moles. 0.02 moles of O2 is the excess. So I'm going to go ahead and write that down now. So we have 0.02 moles O2. This is the excess. This is the total number of car tires. And then we're going to subtract from this the amount of oxygen used in the reaction. The amount of oxygen used. All right? And this is going to give us the amount of oxygen left over in the reaction, which is about 0.005 moles O2 that remains in excess, right? It remains after the reaction is over. Okay? So now I'm going to go ahead and close the video.